Okay, so we will continue on with more stuff. Okay, so what have we learned so far in this class? Huh? A lot. Okay, thank you. All right, just humor me here. Okay, okay, what did we learn last week then? That makes your life.
About random variables.
Random variables.
Binomial.
The binomial distribution, which is a specific type of random variable. Okay, and basically we learned about the random variables based on rules of probability. And why did I say we're learning probability?
To help with inference.
To help with inference. And do you guys remember what role probability plays in inference? In terms of making conclusions?
It determines the likelihood that the results we see.
There we go, exactly. So by understanding something about probability, we can decide if the results or the data that we observe is probable or improbable. Okay, and that's the that's going to play a key role in inference. Okay, so for example, if I play a game of roulette at Las Vegas, and I bet on the color red, okay, about how often should I win? Are you guys familiar with the game roulette? It's got the wheel. Okay, you spin the wheel and then you drop the ball, and it goes around, and then it falls into a slot. Okay, there's 38 slots on the wheel. 18 are red, 18 are black, 2 are green. Okay, and if you bet $10 and you say, I think it's going to land in red, and the ball lands in red, the casino will pay you $10 and you walk away with 20. But if the ball lands in either a black or green spot, the casino keeps your $10. Okay, so on this wheel, there's 38 spaces, and 18 of them are red. So about how often should I win? 18 out of 38, so just a little bit under 1/2. Okay, it's about 47% chance of winning. So if I play 10 games of roulette, about how many games should I win?
4.7.
Okay, 4.7 games. I would win something between around 4 to 5 games, right? That's what I'm expecting to win. Now, if I win 7 games, I would say, oh, I did pretty well. I feel good about myself. Okay, I feel lucky. But if I win 7 games and the casino comes out and says, I think you're cheating, what would you say? Huh?
Yeah, which point?
That I cheated at roulette. Yeah.
How can you possibly cheat at roulette?
Well, they say, maybe something's going on, right? I mean, you saw Ocean's, whatever, 13, using like a weighted ball, okay? So there's something, right? Maybe you're like tilting the, I don't know, whatever. You're doing something, okay, and they say, well, you won 7 games out of 10, and according to probability, you should win around 4 to 5 games. So what would you say?
How unlikely is it that I should win 7?
Yeah, so you could say, no, I can win 7 games. We learned the probability of winning 7 games out of 10. We can figure this out, right? How? Binomial, right? We would use binomial. N is equal to 10. 10 trials. The probability of a win is 47%, or 18 out of 38 to be more precise. And then you go through this calculations, and you can say, based on the binomial model, this is my probability of winning 7 games out of 10. And if I won 7 games out of 10, and you're accusing me of cheating, you'd probably also accuse me of cheating if I won 8 games out of 10, 9 games out of 10, or 10 games out of 10. So according to the binomial model, you would accuse me of cheating this percentage of the time, okay? And I'm not actually cheating, it's just by random chance I happen to win 7 games out of 10, and we can do that. And if you do the calculations, it's like about 17% of the time you would win 7 or more games of roulette if you were just betting on red. Okay. So if so what we're saying is I played 10 games, I've got about a 17% chance of winning 7 or more games of roulette. So that seems entirely reasonable that somebody would win 7 out of 10 games of roulette, right? That doesn't seem unreasonable for someone to win that many games. But if somebody played 100 games and they won 70 games out of 100, okay? And the casino comes out and says, I think you're cheating. Could I use the same argument and say, I just got lucky?
Probably not.
No.
Probably not, right? Okay, I could say, no, I just got really lucky. Well, and they could say, all right, smarty pants, let's find out, figure out the probability of you winning 70 or more games out of 100. And it turns out that that's a incredibly small probability, maybe like 1 in 10,000 or something like that. Okay, and so the casino can either say, I think maybe you were one of the lucky 1 out of 10,000, or I think you're cheating. Okay, kick you out of the casino. Never allowed to play again. Okay. Well, anyway, that's where we're headed, and I'll probably tell the same story again when we do actual inference, and I'll write stuff on the board. But today we're going to learn another random variable. Okay, so this is still in the realm of probability, and it's a specific random variable called the normal distribution. Okay. So this is used to model a specific random variable. All right, and when we say the word model, okay, the idea here is that in real life there's some phenomenon that we're trying to understand, and we're going to try to approximate how that phenomenon behaves using a mathematical model. Okay, so it's like a model airplane kind of gives you an idea of what a real airplane looks like. A normal model or a mathematical model gives you an idea of what some real phenomenon or distribution looks like. Okay. And so it's used to model a specific random variable. Okay, it's the random variable is continuous. Okay, it's continuous. Okay, unimodal and symmetric. It's what we consider the bell curve. So in lay terms, the bell curve. And it looks something like this. So right here is the mean, or our average. It's right there in the middle. And this is the height of the line represents how the probability of getting this particular value. So the mean is the most frequently encountered value. Okay? So values around the mean happen the most often, and then as we get further away from the mean, so if we go high above the mean, the further we get, it becomes less and less likely until we're extremely far away where it's virtually impossible. And then on the other hand, we can go below the mean, and the further we go below the mean, it becomes less and less likely as well. So there's lots of things in real life that seem to follow a normal model. Okay, so examples. Follow the normal model or normal distribution. Human height for each gender. Human height for each sex. Follows the normal model. IQ scores. Or other generally standardized test scores like the SAT, things like that. Those follow normal models. Well, related to human height, lengths of bones in the body, bone length, so your femur or whatever, so bone lengths. Certain animals, their weight or size. Sizes of certain animals. Not weight of humans. I don't know. Okay. So these are these things follow the normal distribution. What are there other examples that you guys can think of maybe? No? Okay. Okay, and the book says cholesterol levels in your blood. Okay. So most things, or not most, but a lot of things follow the normal distribution. Okay, and this is level. So all normal distributions are defined by a mean and standard deviation. Okay, and so because we're talking about a random variable, the mean here, we would use what symbol? Mu, and standard deviation. Sigma. Okay, so let me draw a line right there. So this value right here is the mu. That goes right at the mean. Now, if this entire curve represents 100% or 1, what percentage or what proportion is below mu?
50.
Yeah, 50%, okay? So if I were to shade below, I would have 0.5 is below mu, okay? And another way I could write this is that, let's say, if I were to pick a random variable, or I'm sorry, not a random variable. If I were to pick a random number from the normal distribution, okay? If I were to pick a value from the normal distribution, what's the probability that that value is less than mu?
0.5.
That probability is 0.5. And we would write something like this. The probability that y is less than or equal to mu So if I draw a line over on this side, okay, how much is less than this particular line?
75%.
Okay, well, we don't know. We don't know the exact value, but we do know that it's going to be more than 50% and less than 100%. Okay. All right. So the interesting thing is that all normal distributions are defined by mu and sigma, and once you have those, for all normal distributions, we can kind of scale things based on the standard deviation. So let me just make a large. Okay, if we got mu and I were to travel if I've got mu and I've got sigma, the size of a standard deviation, and if I were to travel one standard deviation above mu and one standard deviation below mu, okay? Then about 2/3, a little bit more than 2/3, about 68% of the total area would be contained between here and here. Okay, so this region here, that contains about 68%. So 68% of the data, I should say about 60% of the data in a normal distribution is within one standard deviation of the mean. If I take this distance, sigma, and I go out again, so I'm 2 standard deviations out. So distance over here. So now I'm 2 standard deviations away from the mean. I have about 95% of the data is within 2 standard deviations.
Is that just a rule?
Yeah, this is for all normal distributions. Okay. And if I go out one more, so a total of 3 standard deviations away from the mean. How much do you think is within 3 standard deviations?
99.
Okay, almost 100%, not quite. About 99.7% is within 3 standard deviations of the mean. Okay, so let's try an example using real numbers here. Okay, so are we familiar with how tall people are? Maybe specifically, let's see, should we do men or women in the United States? We'll do women. And, alright, so does anyone, are we okay with dealing with feet and inches also? Okay, some students don't know feet and inches, but that's okay. Okay, average height of a woman in the United States? Anyone know? Yeah.
It's somewhere around 64 inches.
Yeah, about 5'4", okay? About 5'4", so 64 inches. So we'll just use some rough numbers, okay? So we'll say the mean is 5'4", or because there's 12 inches in a foot, 64 inches. And the standard deviation, for simplicity, I'm just going to pick 3 inches, okay? It's a little bit different than that, but we'll just, for simplicity, we'll say 3 inches here. Okay, so just double check about what percentage of women are taller than 64 inches. About 50%. Okay, now if I go up 1 standard deviation, how tall is a woman who's 1 standard deviation above the mean?
61, 67.
So if she's 1 standard deviation above the mean, her height is 67 inches or 5'7", and if we go 1 standard deviation below the mean, her height would be 61 inches. Okay? And so according to our model, approximately what percentage of women are between these two heights?
68%.
Yeah, so about 2/3 of women, a little bit more than that, are between 5'1" and 5'7" inches. Okay, does that match our intuition about the heights of women in the U.S.? I hope. Okay. Now, if I go down another 3 inches, this takes me to what? 58 and 70. Okay, and so that says about 95% of women are between what? 4'10" and 5'10". And if I go out another 3 inches, this takes me to 55 and 73. That says about 99.7% of women are between 4'7" and 6'1". Okay. Are there women who are taller than 6'1"?
Yes.
Yeah. Are there women that are shorter than 4'7"? Yeah. Okay. But according to the normal model, only about 3 in 1,000 are outside of that range. Okay. Now, of course, this isn't a perfect model, and everybody's different, and so maybe the proportions aren't exactly so. Okay. But the normal model is this mathematical model that kind of approximates and serves as a good approximation for things in real life, such as the height of women in the United States. Okay. All right. Let's. What if I asked about what percentage of women are between 61 inches and 64 inches? About what percentage are between 5'1" and 5'4"?
34.
34%, right? Because if I got about 68% from here to here, I'm going to have 34% in this zone right there. Okay? And what if I said, what percentage of women are taller than 67 inches? So what's the probability that a
30.
woman's height is over 67 inches? Do we know? Can we
About
guess?
15?
About 16%. Okay, about 16%. Can we see that? So if I've got 68% from here to here, right? That means how much is outside of 61 and 67 total?
32.
32% total outside, and half of that 32 is going to be below, and half of that 32 is going to be above. So I've got about 16% above there. Okay, is that all right?
Mm-hmm.
Okay, what if I asked what percentage of women are shorter than 60 inches? Can we answer that? Or is it no? Or yes? What percent of women Okay, well, 60 is not conveniently on any of these breaking lines, right? So, as of this point, we can't answer this question. But what we can do, and this is the amazing thing, is that any normal distribution, when you look at it, if you've got the mean and the standard deviation, they all have the same shape, okay? So if we look at a distribution for the heights of men, okay, which is centered around 70 inches, and also about a standard deviation of 3 inches, we can, that has the same exact proportions when you split them up. So what we're going to do is we're going to look at something called the standard normal table. And we're going to use something called a z-score. So let's talk about z-scores. Okay, a z-score is the number of standard deviations a point is from the mean. Okay, it's how many standard deviations a point or measurement is from the mean. Alright, so let's see if we have this. So for women, the mean is 64 inches.
Mm-hmm.
And each standard deviation is 3 inches. So what is the z-score of a woman who is 67 inches tall?
2/3. I mean, 1/3.
1. Her z-score is how many standard deviations she is from the mean. If she's 67 inches tall, she is exactly 1 standard deviation above the mean, okay? Because each standard deviation is 3 inches. Alright? So what is the z-score of a woman who's 61 inches?
1. -1?
Negative 1. Negative 1, okay? So a woman, so again, for women in the US, the mean is equal to 64, the standard deviation is equal to 3, okay? So a woman who is 67 inches has a z-score equal to 1. 61 inches has z equal to -1. Is that good? Alright. How tall is a woman whose z-score is -3?
550.
55. Okay? So if a woman has z-score -3, her height is 55 inches. Is there any confusion or any questions as to where these numbers are coming up? Yes?
So, as long as it's within one standard deviation, it doesn't matter what, is considered one? For example, the 61 is still considered -1, even if it's not completely set?
Maybe I don't fully understand your question. I'm sorry.
The 61, you said has -1. The z-score is -1.
The z-score is -1 because it's exactly one standard deviation below the mean.
Oh, okay, I'm thinking, sorry, I thought the 60 was the...
Yeah. Okay, yeah. So here's my next question. What is the z-score of a woman whose height is 60 inches? Okay.
-1 1/3.
What is the z-score of, a woman whose height is 60 inches? And you said, well, let's put it in decimal form. Z would equal what?
-1.33.
-1.33333, right?
Bless you. You're welcome.
Okay. Is that alright? And how did we get that? So in our head we just said 60 is 4 inches below 64, and we divided that by 3 and we got -1.33. So I'm gonna say this is the calculation that you probably did in your head. Is that okay? Alright, so let me just ask another one. What is the z-score? So if the woman is 6 feet tall, 72 inches tall, what is her z-score?
2.66.
Okay, 2.66, 2.67. So we did 72 minus 64. That tells us we're 8 inches above the mean. But we don't want how many inches, we want to know how many standard deviations. So I divide that by 3 and I get 2.66, 2.67. If I round up to 2. Is this okay? Okay, so the formula for z is equal to whatever height or measurement you're looking at minus the mean divided by the standard deviation. This is how we get a z-score. And it works both ways. It works both ways. How tall is a woman whose z-score is positive 1.33? Yeah, 68 inches, okay? So 1.33 standard deviations above the mean. 1.33 standard deviations would be equal to 4 inches, because each standard deviation is 3 inches. And if I add that to the mean, I would get her height to be 68 inches. Okay, so if we can turn things into z-scores, then we have a tool that will give us the areas in the table, okay? Or the area in our curve. So let me just clean this up here. Alright, so turn to the back of your book, if you've got it, to page 616. And if you don't have a book, see if you can share with a neighbor, because I just want to make sure everybody can do this part okay. Okay, so page 616, if possible. Okay, so if my z-score is 0, where am I located?
Mean.
I'm located at the mean, alright? So just imagine I draw a vertical line right at z equals 0. How much will be shaded in the table? Not in the table, if I shade to the left of z equals 0.
Nothing.
So if I draw a vertical line right at the mean, how much is going to be to the left? It's a redundant question here. 50%, right? So if z equals 0, you'll notice that in your table it starts off at 0.0 and 0.00. The first number, this is on page 617, the first number is 0.500, right? Should be. Okay? So that represents the area that's shaded to the left of z equals 0. Okay? Now if I draw a line at z equals 0.01, alright? That means I am 1/100th of a standard deviation above the mean. Okay? So to look up that value in the table, I would go to the row that starts off 0.0, but then the column 0.01. Okay, so it's the number right next to 0.50000, and what number is that? 0.5040. Okay, so am I going up 1/100th of a standard deviation? I'm going up about 4 1/1000ths in the percentage that's shaded. Is that okay? All right. Now, if I went up 1/10th of a standard deviation, what is my z equal? A total. Z would be 0.10. Okay. So if I'm 1/10th of a standard deviation above the mean, the number I look up there would be row 0.1, and which column am I looking at? The very first column, okay? And so what's that number right there?
0.8413.
Not 0.8413, that's
55399. Oh, whoops.
0.53 what? 98? Okay. So that is 1/10 of one standard deviation. So make sure all of your decimals are okay. Yes?
Why do you look at this and why do you look at that?
Yeah. So we have to be able to make numbers somehow, okay? So let's just try a few drills here. So let's say z is equal to 1.28. That means I go to row, which row? Row 1.2 and column 0.08. And the number at that intersection, 1.2 and 0.08, what is that number?
0.8997.
0.8997. okay? So if I draw, so how many standard deviations am I away from the mean there?
1.28.
I'm 1.28 standard deviations above the mean, and that means if I were to shade this entire region, I would have almost 90%, 0.8997. So just about 90% would be shaded to the left of z equals 1.28. Is that okay? All right. What if,
I have a question about
Yeah.
this. So 1.28, you're shading the whole thing, it's not just to the mean?
yeah, not to the mean, okay? Because if it's to the mean,
It's 50.
I would have, I can't have more than 50%, right? So it's going from, all the way from technically negative infinity, all the way up to z equals 1.28,
Oh, okay.
okay? All right, what if, I go to 1.28 standard deviations below the mean? My z is then equal to negative 1.28. All right? Where do I go on my table?
Negative 1.0.
Yes, I look up the row, negative 1.2, and I go to the column, 0.08. And how much is there? 0.1003. All right, so I got 0.1003, and that represents how much? This piece in the triangular wedge right here.
10%.
Yeah, 10.03%. Not 10.3, but 10.03. Make sure we don't mess up our decimals. So 0.1003. All right. Do you guys remember how much was to the left of z equals 1.28? 0.8997, right? So the way I can write this, please do not do this, okay? Please do not write z equals 1.28 equals 0.8997. This irks me because 1.28 does not equal 0.8997, okay? You can put an arrow there, okay? And I'm okay with that because that shows you that 1.28 leads to a number 0.8997, but please don't say it equals 0.8997, okay? But what we can do, if we want to be technical, is that the probability that z is less than 1.28, this quantity is equal to 0.8997. Okay. And over here, probability that z is less than negative 1.28 is equal to 0.1003. Do we notice anything about these two numbers?
They add up to 1.
They add up to 1. They add up to 1. Why would they add up to 1?
Because it's 100%.
Because the thing is symmetric. It's symmetric, okay? So what I had before was that z equals 1.28, and I asked how much is over here, okay? And we said this is 0.8997. All right, you guys, this is what we asked last time. So if you can imagine if I took this and I flipped it over, that would give me z equals negative 1.28. And so I would have 0.8997 over here. And when I looked it up in the table, I got 0.1003 over here. And so naturally, this whole thing adds up to 1. Okay? If you try it a few times, maybe it'll click and you'll get it. And if you try it a few times and you still have no idea what's happening, that's okay, all right? So some of us can see these things visually and get it, and others of us, that's not our strong suit, and that's okay. All right, So let's just try a few more. Okay. What if I said I want the middle 95% here. I want this part to be 0.9500 in the middle. Okay. So how much would I have in this table? 2.5% or 0.025. And how much would I have in this one? Also 0.025, right? Can you give me the z that will give me 0.025 in this tail? What is the z that gives me 0.025 in this tail? I should have asked you to find it, but then don't say it. We'll give the other people a moment to find it. All right. Do the rest of you guys see that? That the z that gives me 0.025 in the tail is negative 1.96. Okay. What the difference here between what we're doing now and what we did before, okay, is that before I gave you the z-score and I said how much will be shaded in if I draw a line and I shade to the left. Now I'm telling you how much is shaded and I'm asking you where did I draw that vertical line. Is the difference clear to you guys? So what I'm doing is I'm looking for 0.025 and technically 0.0250 because your table always has 4 digits in it. I'm looking for the area or the z-score that gives me an area of 0.0250. I'm basically asking what is the z that's going to give me 0.0250 here. Yes?
Is there a formula for that?
There's no formula for it because
There's a table.
yeah, we've got a table. Yeah.
So we just have to hunt for the corresponding
Oh, okay.
table?
So the truth is there is a formula, there is an equation, but it's I don't know if you've taken calculus, but basically they're integrating the function and they're finding the area underneath the curve, and they're just finding the limits of integration that give us these things. But you don't want to do it because it's a pain in the butt. So we just use the table. Okay. Okay, so when we do that, we go to the row negative 1.9 and the column 0.06, and that gives us 0.0250.
Excuse me.
Yes.
You mean you had to look for 0.025 here?
Yes, so that entire thing you're looking for 0.0250. It's not that bad because they're all in order, right? Because as you go from left to right, the numbers all get bigger, or if you go the other way, they all get smaller. So they're all arranged in order. So you should be able to find 0.0250 relatively easy. But be careful, okay? This is a common mistake. Common mistakes is that you're looking for 2.5%. 2.5% is equal to 0.025. Okay? Do not search for 0.2500 or 0.0025. Okay? These are drastically different numbers. And okay, you've got to find 0.0250, but countless times I've seen people make that mistake. So don't do that. We get z equals negative 1.96. Okay, so what is the z that's going to be over here? Z is equal to positive 1.96, right? Z equals positive 1.96. If I look that up in the z table, and I go to the row 1.9 and the column 0.06, what number is that going to give me? 0.9750. Why is it 0.9750 and not 95 or something?
Because it's everything to the left.
Because it's everything to the left, okay? Everything to the left. So I've got 2.5% above, 97.5% below. So we have z is equal to 1.96.
Or can you subtract it to 1 or something?
Subtract what from 1?
1 from 10250 minus 1.
Yeah, and you get 0.9750, yeah. But okay, I mean, once you find the negative 1.96, we know that this one's going to be positive 1.96 because it's symmetric, right? Okay, is that alright? Finding the positive 1.96 and the negative 1.96? Okay. Earlier today, what did I say? About 95% is within what? Two standard deviations of the mean, okay? The truth is that exactly 95% is within 1.96 standard deviations of the mean, okay? So, exactly 95%, or just about exactly 95% is between 1.96 standard deviations of the mean, but that's close enough to 2 that we just round off and say about 95% is within 2 standard deviations of the mean. So if you go out to 2 standard deviations, which you're just a tiny bit further away from the mean, you're going to get, what, a little more or a little less than 95%?
That way? A little more.
A little bit more, right? So if I go out 2 standard deviations rather than 1.96, I'm going to get just a tiny bit more than 95%. Okay. Is that okay with you guys? Okay. So now that we are equipped with the z-table, and we know how to find z-scores, we can go back to answering this original question, which I got rid of. I said, what is the z-score of a woman whose height is 60 inches? And the original question is, what percentage of women are shorter than 60 inches? What percentage of women are shorter than 5 feet? I don't know. Let me just check this again. Sorry. All right. Sorry. Okay. So again, I should just say, don't say anything yet. But the answer is 9.18%, or the proportion is 0.0918. Alright, now how did I get that? Okay, I said, we said the height of women, the mean, is 64 inches. The standard deviation is 3 inches. So a woman who's 60 inches tall has a z-score of negative 1.33. Okay, technically 1.33333, but because our z-table only gives us 2 decimals up to 2 decimals in the z-score, I'm going to just round off to 2 decimals, and I get negative 1.33. When I look up negative 1.33 in the z-table, that gives me an area of 0.0918. Okay, so that means if I were to draw a picture, a lot of times drawing a picture helps. So my mean is at 64. This woman is 60 inches tall, and I'm asking how much is over here. Well, when you look that up in the table, it says 0.0918. So about 9.18. So about 9% of women are shorter than 5 feet tall. So the probability that a woman's height is less than 60 inches is equal to 0.0918. Alright, so then what percentage of women are taller than 60 inches?
0.9072.
9082. Yep. So if I said what percentage is taller, I'm just asking for what's over on this side. Okay? So that's going to give me 1 minus 0.0918, which gives me 0.9082. About 91%. Does that make sense?
Mm-hmm.
Alright, if I'm talking about percentiles, I could also say a woman who is 60 inches tall is in the what percentile? Are we familiar with the term percentile? Yeah, all we would say is she's in the 9th percentile. Okay? So the percentile is basically the percentage that's that has heights or scores or whatever, the percentage that's lower than a certain number. Okay? So if 9% is lower than a certain number, that person's in the 9th percentile. If 33% of the population is lower than a certain number, that person's in the 33rd percentile. And so this often comes up, I don't know, if you have a baby or something, and they're taking all these measurements, like head circumference or something like that, they say, oh, your child is in this percentile. Okay? So 50th percentile means your child is right in the middle. 50% are lower, 50% are higher. If your child is in the 10th percentile, 10% is lower, 90% are larger. If your child's in the 80th percentile, 80% are lower, 20% are larger. So if I say what percentile is someone in, it's basically the exact same question here. What percentage of women are shorter than 60 inches? It's just dressed up a little bit different, right? Same exact question. So what is the percentile of a woman who is 60 inches tall? So you get Z is equal to same thing. You get -1.33, which gives us an area equal to 0.0918. So she's in the, and if you want to get technical, you can just say 9.18 percentile. Or you can just say 9th percentile, that's fine also. Okay, so let's try a few questions. Okay, so let's do the height of men. Men in the US, okay, height follows the normal distribution. The mean is equal to, you guys know, average height of a man in the US?
5'11".
5'9", 5'10". We'll say 5'9" and a half, okay? 69.5 inches. Standard deviation. Let's just keep things simple and we'll say 3 inches. Okay? It's a little bit different. Okay. Sometimes, because the normal distribution shows up so frequently or whatever, we'll have shorthand and we'll say male height. Okay. And this tilde, it says follows or comes from this distribution. And we write n for the normal distribution, and we write 69.5 comma 3. This is shorthand for writing all of this. So you might just see it in this form. Okay, so I'm going to ask a few questions. I'm going to say, what percent of men are taller than 6 feet, 72 inches? We select a random man. What is the probability? He is shorter than 67 inches. And we'll try one more. What percentage of men are between 5'10", that's 70 inches, and 6 feet. 72 inches. Okay, so I'll give you guys a few minutes to work out these answers. See if you